you doing? You look like you got some problems.
Oh, that burrito I ate this morning was not sitting well.
Oh, burritos, that causes gas sometimes.
Yeah.
You must be having some gas problems.
I'm thinking so.
Huh. You know what we're going to talk about?
It was so good, though. Oh.
Yeah, well, it might have been
It's
good.
like the size of my head. Had chicken and beef and beans and rice and green chili on top.
You know, Mr. Sams, we're going to be talking about Boyles and Charles and Gay-Lussacs Laws. You know,
Oh.
Boyles Law has to do with like pressure and the volume. So you're probably feeling some pressure inside of your gut. Yeah, and so that's caused by gas.
Increasing the volume of my gut as well.
Yeah. Yeah, so why don't we talk about that today?
Okay.
All right, so let's go ahead and do that. So, guys, we're going to talk about gas laws today.
Yep.
So today, Mr. Sams, we're going to learn about Boyles, Charles, and the Gay-Lussacs Law.
Good. I feel better now.
Do you?
Yes.
Wonderful. You must have relieved some of the pressure.
Perhaps.
Yeah, okay. So our goal is to find about the relationship between pressure and volume of a gas.
All right.
And when you try to find that, that's something called Boyle's Law.
Okay.
So if you increase the pressure, so let's say we have a fixed quantity of gas, and I increase the pressure.
Okay. Pressure goes up.
What's going to happen?
I'm pretty sure the volume's going to go down.
Pressure's up, volume down?
Yeah.
So I drew it wrong.
Yes, you did.
Oh, okay.
Yeah, I always think of it like a piston. If you shrink it down, you decrease the volume, and the pressure gets more inside that container.
All right, so here's what he's saying, guys. If I have a piston right here, okay, and I have a plunger right here.
Think of like a bike pump.
Like a bike pump. Yeah, bikes. I like bikes.
Bikes.
Okay, and then if I do this in that plunger and I push it down harder, because I apply more force,
right.
The same gas down here and the same gas down here, this, of course, will have less volume, higher pressure.
Correct.
Okay, this is called Boyle's Law. Okay, now, you know, Mr. Stevens, this summer I had a kind of interesting experience. I rode my bike up a mountain.
As you do often.
As I do often,
yes.
I know. But while I was doing that, I conducted an experiment.
Oh.
So I think we should watch the Mr. Bergmann Bike Up the Mountain video.
Okay.
And see how this applies to what we've been learning.
Okay.
Okay. Go. Here I am at the base of Mount Evans. Now, if you look back up here, you're going to see a bunch of mountains, and I'm about to climb that mountain here. But I have myself a bag of Pringles Minis, and I want you to notice the bag's kind of roughly like this, or you can push it down. It feels a little full, probably, compared to what you're probably used to if you live at sea level. But think of the gas particles striking this all of a sudden. But we're about to climb on our bicycles the highest paved road in America, which is the Mount Evans Road, and we're going to see what this bag looks like, and it's actually an application of Boyle's Law. So we'll see you there in a few minutes, or hours. Rolling. And we're on the highest paved road in North America. Pikes Peak Highway, riding up. Mr. Creek, what altitude do you think we're at?
We're right around 12,000 feet.
12,000 feet. So, now look at my Pringles potato chip bag. Now, compared to what we saw, it's totally full. Boyle's Law in action. How's that Boyle's Law? Well, you see the gas inside, the pressure is the same. I'm breathing hard. The pressure is the same, but the external pressure at this high altitude is lower, and therefore the molecules, here I'll try and show this. Okay, let's pause here. The molecules that are hitting this, well, there's fewer of them because we're at a higher altitude. But the molecules on the inside, the air molecules on the inside, they're the same number. Therefore, the bag expands. Now, we're going up there to the top of Mount Evans, 14,200 feet, I think. When we get there, I anticipate that this bag will be either fuller or possibly it will explode in my backpack and I'll have a mess. Let's see it. I'm at the top of Mount Evans. It's a windy day, and I got my bag of Pringles Minis. Look at how big that is. Totally full. I think it looks here because of the Boyle's Law. Not very much air up here, even though it's windy, so it caused the potato chip bag to expand. You know what I ought to do? I should eat some.
You actually had to get off your bike to talk to us there for a while.
Well, you know, there's a problem. There's not as much oxygen up there either.
And that's because there's lower pressure up there.
That's right.
And the lower pressure at the top of the mountain made the bag of chips get a greater volume. So pressure was down, volume was up.
Exactly.
Okay.
Exactly. So that is Boyle's Law. This is actually, folks, what you do, copy this down. This is the graph of Boyle's Law. So pressure up and the volume goes down. This is the graph. All right? This is said to be inversely related. And the way we know that is if you plot a graph of volume versus 1 over the pressure,
you get a
straight line. And that is the equation. Now, actually, the equation is this. The meaning of the graphs, pressure is inversely proportional to volume, which we said already. All right. If one variable doubles, the other one is half. So a lot of people want to say up and down. That's true, but the key thing, students, to understand is that if you double one variable, the other one will cut in half. Now, Mr. Sams, what would happen if I were to triple the pressure?
The other one would go down by a third.
Yeah. So it's the inverse, the reciprocal, guys.
Or not by a third, to a third.
To a third,
original
actually,
ones. Yeah,
that's correct. Now, there's actually a chemical, or not a chemical equation, but an equation is P1 V1 equals P2 V2. Right?
Okay, so P is probably pressure.
Yeah.
V is probably volume.
Yeah.
What do those little 1s and 2s mean?
Well, the first one is the initial condition. So when I was at the bottom of the mountain, I could have measured the pressure and the volume.
Okay.
And then at the top of the mountain, the pressure would be different, and therefore the volume would be different. So it's just like the initial conditions. 1 would be at the bottom of the mountain, and 2 would be at the top of the mountain.
So initial and final, you're implying that a change has taken place to that gas.
That's exactly right.
Okay.
Okay. So let's actually do an example. So a 2-liter balloon is taken from Woodland Park, pressure of 0.75 atmospheres, to the top of Pikes Peak. Well, this is Pikes Peak, but I went up top of Mount Evans.
Okay,
The same idea,
close.
really. What's going to happen to the balloon? Not a bag of Pringles, but a balloon. Actually, let's. So here we have the balloon in Woodland Park, and here's the balloon at the top of Pikes Peak, right? So let's actually do it on a blank screen here.
Okay.
Okay, so let's do that. All right, now what I want to do. So here's our problem, Mr. Sams. I got our calculator. In fact, everybody, you should get your calculator out.
And
okay.
Yours probably doesn't have feet, but ours does.
Yeah, we've got the cool calculator of the feet. All right, so what I want you to do is you're going to write P1 and then V1. So let's determine what these are.
Okay.
So we have a 2-liter balloon. So
Okay,
what is that?
2 liter is a volume.
All right.
And that's its initial volume.
So that's
we're given
2 liters.
Down in Woodland Park.
All
Okay.
right. In Woodland Park, pressure is 0.75 atmospheres,
Okay.
which is about right where we live.
Yep, pretty close.
So I'm just
Depends on
writing
the day.
down what I know. And then there's going to be a P2 and a V2.
Okay, so what else do we have? We go to the top of Pikes Peak, so a change has occurred.
Yeah.
We're at a different place with a different pressure.
So the pressure is 0.54.
Pressure is 0.54 atmospheres. So we have a different pressure. Now, pressure went down. So I'm going to guess that the volume is going to go up.
Yeah, so this is what we're trying to find, and we should predict it goes up. So we're going to use the equation P1 V1 equals P2 V2. Now,
Okay.
P1 is, we're just going to plug in our numbers.
Plug and chug. 0.75
0.75
atmospheres.
atmospheres times
2 liters.
2 liters is equal to 0.54 atmospheres times
V2.
V2.
And we're going to solve for V2.
Well, this is easy, Mr. Stern. This is like easy algebra.
It is.
You just divide both sides by the number next to the V2, right?
Yep.
0.52.
5.4, actually.
Oh, 4?
Yep.
Whatever it is. Okay. So now I've got my trusty calculator, so it's going to be 0.75 times 2 divided by 0.54. And you said it's going to go what?
It should go up.
Up. And guess what you get? 2 points. So V2 is 2.77 or 78 probably the sig figs 78 liters. So
Okay.
it went from 2 to
2.8. Yeah, so it went up, so that makes sense. The
Yeah.
answer makes logical sense.
Well, and we
I'm
saw that
assuming
with the
that.
Pringles potato chip
Right,
bag. It
exactly.
went up, didn't it, as
Yeah.
we saw it. All right, so that's